Savage Hunter, Aliens vs. Predator, with awesome new Predators. Clan Leader attacks with whipping dreadlocks. And Stalker, glowing in the dark, fires his spear. Suddenly, lifting up his attack spikes, the wild boar alien charges. And the ferocious mother alien in her monstrous hive traps Spiketail, then covers him in ooze.
Ooze 'em!
Who will survive?
Alright, here we go.
Aliens
Let's
Predator.
check out the next section on Radians. You may be wondering, Aliens vs. Predator, classic movie. I actually never saw it, but I saw Aliens and I saw Predator. I imagine you pair them together, it's going to be amazing. So what does it have to do with anything with math? Well, what we're going to do is, we're going to compare degrees versus something new here called radians. This is probably going to be new for you. So we're doing degrees versus radians. We're doing, instead of AVP, we're doing DVP right here. So we're used to like the alien. It was the original. You had the alien. You know that's our degrees. That's our comfort food or whatever. We know what that is. Like, we use that. Radians is the new one. Is it better? Is it worse? I don't know. It's like comparing alien versus Predator. They're both cool. They both got their strengths. They're both great. So what we're going to do is check out Radians. Going to show you what some of its strengths are and see why it can be better than degrees. So that is our ultimate goal, is to move on to a new way to measure angles. So we're so used to saying, yeah, that's a 30-degree angle. We're going to find a new way to measure it right now. Here we go. Wait a minute. This has to do with metric time. So I want to get this idea of thinking differently here. So let's take a look at this. Before we get into measuring angles, let's look at metric time. So check out this clock. Metric system is so nice because it's base 10. We have the old Babylonian time. Everything's based off of this 60 idea, 60 minutes, 60 seconds. Could we do the same thing with a metric day? Could we have, say, 1 day, a tenth of a day, a hundredth of a day, a thousandth of a day, these different things here using the metric system? Like, why don't we say a cent a day? Because that's weird, but don't freak out. Check this out. Let's say I'm going to watch an episode of Gossip Girl. Love Gossip Girl. If you're going to do a 30-minute episode of Gossip Girl, how many centidays is that? Take a second to pause and just think about that. See if you can come up with that answer. It's kind of tricky. Good luck. All right, one way to do this would be, say, okay, I'm going to do it two different ways here. So think about 30 minutes. We are going to get into some serious factor labeling in the next section. So we can factor label this. We know there are 60 minutes in an hour, and we know there are 24 hours in a day. So we're okay with that. 24 hours 1 day. 1 day in our normal time that we're used to is so easy for us is really what? Well, I want to go to centidays. How many centidays? Well, there should be 100 centidays. Can I call them CDs? 100 centidays makes up a day. So I can do this as a conversion with my factor labeling. And remember, the whole point of this is things cancel. My minutes cancel. Boom, boom. My hours cancel. My days cancel. So I'm left with, I changed all the labels to the centidays. And then remember, you multiply across the top and divide if it's on the bottom. So 30 divided by 60 divided by 24 times it by 100. Did anybody get 2.083 repeating? If you did, you're an absolute boss. Boom. This is going to be 2.03 what? Centidays. I'm going to call it CD. I don't know if that's legal. I don't know. But that's my centidays. So a 30-minute episode, yeah, I'm going to watch an episode that's going to be 2.083 centidays. So factoring label would work. Another way that's probably quicker is just to come up with some kind of conversion factor. And that's really what I'm going for here. So if you think about it, remember, there are 60 minutes in an hour, 24 hours in a day. So if we multiply that out, how many minutes are actually in a day? So, and it's kind of what factor label does here. There are 1,440 minutes in one single day. So really, if there's that many minutes, how many, I spelled minutes wrong there. That is not good. There are 1,440 minutes in a day. A cent a day is a hundredth of a day. So can we take that and divide it by 100? That's a hundredth of a day. So what does 1 cent a day equal? Well, it's going to be, what, 14.4 minutes is 1 cent a day. There's my conversion. Just like 1 inch is 2.54 centimeters, something like that. I just want to throw something weird and new at you. But don't freak out. We just got to get these conversions and we're good to go. Now I can convert anything. I want to know how many centidays. Boom, I've got a conversion. Excellent. So if you want to say how many minutes is that, we could double check our answer. Let's just double check it. Might as well. We could take our answer of 2.083. That was in centidays. 2.083 repeating, so I'm going to do it a couple times. And I'm going to times it by, what's the conversion? It is 14.4. Does that get us back to, yes, we did it right. So I'm converting back and forth. Exactly what we're doing today. All right, let's leave metric time alone, even though it's so cool. There's a big push to bring it back. Not bring it back, it was never here. To start it. All right, let's review circles before we're kind of leading into the radians here. So we looked at conversions. Now let's look at reviewing circles. Circumference. What do we know about circles? Well, we know the radius. Boom, bring that bad boy out. Hopefully remember this. This is the central angle in here, and then this is the arc out here. So the arc is the piece. I should have color-coded this. It's this piece right here. That is the arc. And this has to do with circumference. Remember, circumference is 2 times pi r, which is really pi times the diameter. So same thing here. So we're going to do a lot with circumference. That's where our radians are going to come from, actually. They're going to come from circumference. So if I give you something like this, the arc length, if I want to talk about the arc length here, well, the measure of the arc length is something like 60 degrees. That we don't use very often, the measure. We actually use the distance. So we're going to find the actual length of it. Like if I walked from here to here, how far am I walking? So for arc length, I'm not sure if you know this, we use S. So we're saying S. And how do I find this part right here? Well, arc length is pretty good here. If I think about the entire circumference, so can I find the entire circumference of this circle? Whoa, yes. We can find it by saying 2 pi r, or so 2 pi r. And let's go ahead and do it. That's going to be 2 times pi times 8. So I know the circumference is 16 pi. And we're going to try to leave things in pi. We're not going to approximate. We're not going to make these decimals going to be 16 pi. So I've got this, but that's the whole circle. I don't want the entire circle. How much of the circle do I want? Well, I want 60 degrees of it. Well, think about this. You're dividing this up 60 degrees, like a little pizza here. Well, what is this? This is 1/6 of it. So we're actually going to say I only want 1/6 of it. Or you want what? You want 60 degrees out of 360. That is 1/6 of the circle. So I'm going to take 1/6 of it. And when I multiply this out, can I multiply this out? Sure, 16 pi times 1/6 is 16 pi over 6. So that is actually the formula. You take 2 pi r, you times it by the central angle over 360. So that's how we find arc lengths, or S, right there. So there's the actual formula. Can I reduce this a little bit? Sure. What is this reduced to? Well, it looks like 2 goes into that 3 times, 2 goes into that times. So we're looking at 8 pi over 3 is my distance here. So if this is in centimeters, this is 8 pi over 3 centimeters. And again, I want this exactly. I don't want to round this to a decimal. I'm going to leave it as 8 pi over 3 as my arc length. Holy cow, that's just review. So hopefully that rings a bell a little bit. And what is good about this? Well, it's going to lead us up to radians. You're probably thinking it's about metric time you did this. Felt like 100 centidays to get to this point in the video. All right, I'm going to stop. I'm going to stop. That's even too much for me. All right, so we're going to talk radians. So again, I put this circle here just to make sure we know. We're going to call this theta. That's the central angle. Definitely know the radius, and S is how we say arc length, the distance from here to here. So here's the formula. Jot this down and have it. This is what a radian is. A radian is the angle equals the arc length divided by the radius. So let's put this into play. No, I even wrote out here for you. Look at that. Let's see what happens. So I got the same problem here. We solved this, yeah? On the last slide, we said this was 8 pi over 3. So right now, this is in degrees. You know, this is great. There's 60 degrees. I want to use this formula to see what that is the equivalent of. Let's say I didn't know this. I'm going to hide it for right now and say, hey, that's theta. So I want to know what theta is, this angle, and now it's going to be in radians. To find it in radians, I'm going to say, okay, what is the angle in radians? I'm going to take the arc length, 8 pi over 3, because it's S over R, and R is 8. Excellent. So I've got a fraction and a fraction. Remember, how do I solve these fractions and fractions? Well, you got to flip the bottom fraction and multiply. So 8 becomes 8 over 1, which is 1 over 8. And then what happens here? My 8's cancel. So I'm looking at 1 pi over 3. Holy cow, that is huge right there. So if I were to write this in radians, that is what the angle is. And these angles are going to have a lot of pi in them. Pi over 3. A lot of times it's going to be a pi. That is a radian. So instead of saying 60 degrees, we're going to say pi over 3. Don't freak out. That's just like saying 30 minutes is 2.083 centidays. This will get easier for you than probably the metric time. So these are now equivalents, and this is now my conversion. I now know 60 degrees is pi over 3. An easier conversion is probably this, a straight line. Remember, if this is 60, 120, this is going to be to 180 out here. It's kind of labeled kind of weird here. Let me fix that. So really, these are all 60 degrees. So I've got 60 plus 60 is 120, plus another 60 is 180. So I've got pi over 3 plus pi over 3 plus pi over 3. So what is a 180 degree angle? 180 degree angle is pi over 3 plus pi over 3. What's that? Pi over 3 plus pi over 3 plus pi over 3. Well, they're thirds. It's just pi. Oh, there it is. There is the nice conversion right there that we're going to use to convert degrees to radians. Excellent. So that is a radian, arc length over radius. Excellent. So my goal, hopefully, in this section is to really get you think in terms of radians. So I want to kind of force you to think in terms of radians. So a lot of time we're thinking about this circle. So degree, we have this same thing if we're plotting angles on our xy coordinate. But it's nice to think about that circle that came up with things, the arc lengths and whatnot. I think that helps kind of put it in perspective. Definitely going to help in the future. So I got some problems here. Let's think about graphing these angles, and I just want to know what quadrant they're going to fall in. So we're so used to saying, in degrees, this is 90 degrees, right? There's my right angle. Well, what is this is 180. That's degrees, but what is 180? Remember, that's my conversion. This is really pi. So that is a pi angle right there. So what is 90? Well, it's half pi. Boom, it's half of 180, right? So it's half of pi. So if you were thinking about this is 3.14. This is 1.57 cut in half. So I go all the way back around, if I do a circle is 360, or it's 0, we can start 0. Well, what is it in this? If I do all the way around, you're actually doing 2 pi's. 2 180s, you're doing 2 pi's. So what is this mystery one here? If this is a half, this is 1, well, this is 1.5. So we call that 270, but 1.5 is the same thing as 3/2 pi. So if you can convert all these over here, now we got to think about where does this fall. So 2 pi over 3. So 2/3 is not a full pi, is it? No, it's not a full pi. So it's somewhere, but it's over half. 2/3 is bigger than a half a pi, less than that. So it's somewhere in this second quadrant. That is 2 pi over 3, that angle right there. Is that crazy? How about 7 pi over 5? So if I'm going to do 7 pi over 5, I got to think about, well, is it bigger than pi? Sure, it's bigger than pi. It's like saying 1 2/5 pi. I've got one whole pi, 5 over 5, plus 2 other chunks, so I'm past pi, somewhere down here. Boom, this is going to be third quadrant. Why don't you try the next two real quick, see how it goes. All right, negative pi over 4. I'm thinking for negative pi over 4, that's not quite half a pi. That's 1/4 of a pi, but it's in the negative direction. So you went down this way, you went down this way, negative pi over 4. Boom, that is going to be fourth quadrant. And it looks like I've hit second, third, fourth. Did I go back to the first? I don't know. Oh, this one looks tricky. So we've got this 19 pi over 7. So think about that. How many times is 17? How many times is 7 going to 19? It goes in there twice, right? It goes in there twice would be 14 pi with 5 pi over 7 left over. So let's think about what is going on here. So, all right, maybe it's easier to think about this. If I had 7 pi over 7 plus 7 pi over 7 plus what's left over, that's 14 pi, 5 pi. Maybe this shows a little better. So this is what? This is 1 pi plus another pi. That's 2 pi, and what's left over? 5 pi over 7. I guess this would have shown it okay. I think technically I should probably put that pi on the outside. 2 5/7 pi. Either way, they're both mathematically correct, however you want to see it there. So how do I do this? Well, I go 2 pi plus 5/7. What is 5/7? Oh, this is tricky. Is 5/7 bigger than a half? It is bigger than a half, so it's going to be somewhere over here. So my angle is going to end up in the second quadrant. I did not end up in the first. That is the last one right there. Excellent. So I want you to kind of think in terms of radians. Ooh, that's cool. That's interesting. Now let's get down to the just crunching numbers. Here we go. So we're still got those aliens and predators going on. How do we convert this? Well, actually, this is great mathematically. If my conversion is what? I know that 180 degrees is pi. So we kind of looked at these conversions earlier. I like this conversion because what's canceling here? Your degrees cancel. So you're actually left with 210 pi over 180. So that is fantastic. I'm going to get rid of this. The picture's kind of freaking me out a little bit. This is great right here. Can I reduce it? Sure, 30 goes into both of these, doesn't it? 30 goes into the top 7 times. and 30 goes to the bottom this time. Now some people write, I like to write 7 pi over 6. You are more than welcome to write this. These are equivalent, but most people go with this one right here and put the pi on top. So when you see this pi, we're thinking radians, and we're good to go here. How about the next one? Same thing. It's always the same conversion. 180 degrees is what? It is pi. So we kind of showed that earlier. So now I'm looking at this. And again, it's just a matter of reducing. What number goes into both of these? I think 45. I'm hoping 45 goes in there. Yes, 45 goes into the top, what? 3 times? 45 goes into the bottom 4 times. So this is 3 pi over 4. And then the finale, you want to try it real quick? Pause, try. Go for it if you're interested. All right, hopefully you got 88 pi over 180. And it's just a matter of reducing. You can start with 2 or 4 to kind of get these things going. Let's try 4. So 4 goes into this 22 times. 4 goes into the bottom 45 times. I don't think you can reduce it more than that and you're good to go. Here's a nice little trick if you want to check your answers. I was going to say if you're lazy and didn't want to do the work. No, checking. If I'm checking the answers. If I have 88 divided by 180, you can put it into your calculator. It's going to tell you the decimal version, but then come back and just math frac it. I love the math frac. If you hit math frac, it is 22 over 45 pi. So great way to check your work for reducing these. Make sure you got the most simplified form. Awesome. So that's converting to radians. How do I go back to degrees? So it's the same conversion, except what happens now? Remember, to cancel, the degrees had to be on the bottom. That's why they canceled. So what happens here? The pi has to be on bottom. So the pi is going to be on bottom, the 180 is on top, and what's going to happen? The pi's cancel. So I'm leaving radians, I'm entering degrees. So 3 times 180 is 540 all over 4. And then does that reduce? It does. 135 degrees. Excellent. So we got 100. Wait a minute here. Look at that. Look what I just did. These are the same problem. I hope you got that conversion. That would have been embarrassing if that wouldn't have worked. We converted that one back and forth. How about this next one? You could write it like this, but normally we're going to see 5 pi over 3. And we're going to go ahead and convert this bad boy. So the radians are on bottom. Degrees are on top. The reason is so they can cancel. And now we're looking at, what is that? 900 degrees over 3. So what does that really give you? Divide that out. That should be 300 degrees. Excellent. If you want to try the last one real quick, go for it. All right. Hopefully you got 20 pi over 9 is 20. Excellent. So yeah, that's converting back and forth from radians to degrees. Fantastic. Last one right here. So this is where it's going to get weird, is now let's start using radians. We're going to use radians the rest of the year. So the sooner you guys can start thinking about radians, the better. Like, they're not going away. It's not like, oh, I'll just get through this master check or this test. We're going to use it the rest of the year because it's easier for graphing and some things coming up where you actually have to use it. So the sooner you can start thinking about it, 7 pi over 4. So we kind of flirted with this idea before. Remember, this is like saying 1 3/4 pi. So I'm going to go 1 whole pi. So we got to think about this as pi. I'm not even going to write the degrees on here. Pi over 2. This is 3 pi over 2 and 2 pi. So that's how we're going to label it. So I'm going to go 1 whole pi plus 3/4 pi. Remember, this is another half pi, so 3/4 pi is beyond it. So I'm going to graph it like this. This is 7 pi over 4. If for some reason you were just freaking out, or how about this? Let's not phrase it like that. Let's say you're going to check your answers. I want to check my answers. What could I do here? Well, man, just go ahead and convert it to degrees. Like, no problem. You can convert this to degrees. You've got 7 times, I don't know, I'm going to cheat and use a calculator on that one. 7 times 180, 1260. Divide that by 4. Is that 315, I'm guessing? I hope. Yes, it is 315 degrees. So I can say, oh yeah, 315 degrees in my degree mindset. That's maybe a little bit easier to see. Yes, that is 315 degrees. So that is a nice check. Don't do that first. Try to graph it and then check it. I'm cool with that. Awesome. So how about naming coterminal angles? Remember, this was no problem for you. If I gave you negative 200 and you wanted a coterminal angle between 0 and 360, what'd you do? You added 360. And you said, yeah, 160. Not a problem. Do the same thing with radians. Now instead of 0 to 360, it's 0 to 2 pi. Big difference there. So what are we going to do? We're actually going to add 2 pi to this to try to get it above 0. So this can get freaky for people here. Can we add these fractions? Yes. To add a fraction, what do you got to do? Well, you got to say everything's a fraction. It's 2 over 1. You need the common denominator. So put over 1. Common denominator is 6, so multiply the bottom and the top both by 6. So I'm looking at negative 11 pi over 6 plus 12 pi over 6, and that makes sense. 12 pi divided by 6 is 2 pi. So now I can add them. Negative, positive, that gives me 1 pi on top. That gives me pi over 6. So excellent. So get used to adding these things in terms of pi. I think it was our quick review or our something skills, review skills, to kind of get us ready for this. Excellent. Again, this is something you can convert to degrees and check if you wanted to. How about naming every coterminal angle in the world? First thing we gotta do is name this angle. Now this is where it gets a bit tricky. So I'm thinking about this. Boom. I'm going around this way. So I know it's going to be negative. I know it's going to be bigger than negative pi. So if this is pi over 6 this way, what is this chunk right here? Well, if that's pi over 6, you know, that whole thing is a half a pi. So I've got half a pi minus that pi over 6 chunk equals what? Well, you got to get the common denominator. Pi over 2, you know, really multiply this by 3 to get the common denominator. We're looking at 3 pi over 6 is half a pi minus pi over 6. That's going to give me 2 pi over 6, which is what? Reduce it pi over 3. So that reduces 1/3. Awesome. So that chunk left over is pi over 3. So what am I looking at here? This angle is going to be negative pi. And then I got to add on, well, let's not worry about the negative yet. It's pi plus this pi over 3. Holy cow. So I went past pi by pi over 3. So let's not add the negative yet. That's going to freak us out here a little bit. If I combine these and add them together, remember, what is this? Pi is really 3. That's a nice easy one for the common denominator. It's 3 pi over 3. That's just 1 pi. And now I can add them. So what is that? That is 4 pi over 3 when I add them. And now it's really in the negative direction. So holy cow, I'm running out of room. That is negative 4 pi over 3. That's the right direction. Negative pi plus another third pi more is negative 4/3 pi. But what am I going to do if it's all the angles in the world? What if I would have run around twice or 3 times? I have to add. I'm not adding 360 like we did last time. I'm adding 2 pi n. And remember, you got to say where n is an integer. And this problem is awesome. Circle that bad boy right there. There's the answer to this one right here. So it's negative 4/3 pi plus 2 pi n. Again, you could have said, oh, well, I know pi over 6 is 30 degrees. And you'll get to do this so much that you'll know quickly, like, I think of pi as 180. What is 180 divided by 6 is 30 degrees. Boom, I know that's 30. So if that's 30, I know this is 60 because it's a 90-degree angle. I know this is 180. 180 plus 260 is 240. So you could convert this all into degrees and then take 240, convert it back to radians. You're going to end up with this. But that's just, again, a great way to check. Awesome. I'm going to end with a little clip from The Simpsons here on metric time and just the metric system and all. I hope that this mastery check goes well for you. Peace out.
Okay, next item of business is our weekly progress report. Principal Skinner, how's your transportation project coming?
Oh, excellent. Not only are the trains now running on time, they're running on metric time. Remember this moment, people. 80 past 2 on April 47th. It's the dawn of an enlightened Springfield.
Dear God of England, please let me go. In return, I will spell the word color with a U, and I will use the metric system with every cubic milliliter of blood in my... Oh, I can't do it. It's so stupid.